Okay, students, this will be the last part of the notes. We're going to be talking about fluid flow and Bernoulli's principle. And in this part, we're going to start using the ideas that you've learned in the past of kinetic energy and conservation of energy. So if you understand conservation of energy, this will make a lot of sense. So let's get started. So I've got here a pipe. And in the pipe, there's a velocity which is flowing to the right at a velocity that I'm going to call velocity 1. Now this pipe has a cross-sectional area. You take the radius, pi r squared, and you can figure out the radius if it's a round pipe. And so we call that area 1. But now the pipe becomes narrow. And so the narrow part of the pipe has area A2. And in order for so much fluid to pass through the narrow pipe, its velocity has to be higher. And so I wrote here that velocity 2 is greater than velocity 1. So the fluid has gotten faster in this narrower part. And as you know, 1/2 mv squared, right? The kinetic energy will go up. The kinetic energy increases. Now, here's we have to change gears just a little bit here. We have to think about the pressure and the units of pressure. And here's the amazing thing. Pressure, which is in newtons per square meter, has the same units as the density of energy. So energy density, okay, energy, which is in joules, per unit volume, which is in cubic meters. And then I've got the proof of that down here. Newton times a meter is a joule. And so if I multiply the top and bottom of this by mass, by length, by meters, then I automatically get joules per cubic meter. So bottom line, pressure is density of energy, energy density. And yeah, so pressure is a kind of potential energy. Now, coming back to the speed change here, it creates a very interesting thing, or several interesting fluid phenomena. So the first one is Toricelli's law. And Toricelli actually originally had a different demo. My version, my picture here is a little easier than the demo that Toricelli did, which involved parabolic jets of water. But anyway, the point is that if I have a container with a certain depth of water, and then I have a little pipe, a little tube, and the water squirts up, the energy density here turns into, so here it's energy density, potential energy density. But now when it comes out of the container, out of the hose, there's nothing to hold the pressure in. And so the potential energy becomes kinetic energy. And that kinetic energy is just enough to carry the water stream up to the original level that it was at. Okay, so that's Toricelli's law. Okay, so let's go on now to Bernoulli's principle. And I decided that I would show you the effect of Bernoulli's principle, and then we can get into the math of why it happens. So I brought up one of the PhET simulations, and let's make it go. So what you've got here is a pipe, and going from left to right is the flow of water. And I mean, normally you wouldn't see the water flowing, right? Water is clear, but the people who wrote the software added little red dots to represent the water molecules. So now I can put a pressure gauge in the pipe. And okay, so we've got it at a certain speed. This is the pressure of the water. Now what I can do is make the water go through a more narrow pipe like this. I'm now making the water go through a more narrow pipe like this. And now, okay, now look at the pressure here. It's 120.7. Now I bring the gauge to where the water is flowing faster. And look at that. Where the water goes faster, there's less pressure. So Bernoulli's principle says that if you make a fluid move faster, it's going to have a drop in pressure. So why is that? Okay, so now let's see the math explanation for that. Let's go to my notes. Okay, so recall that I said that the units of pressure are the same as the units of energy density. That comes and plays a role here. So I've got a pipe, and I've got water flowing through it, and the area of the pipe is getting smaller here at this place. And in order for the water to actually make it through the more narrow pipe, the water has to move faster. It has to have a higher velocity. So velocity 2 is going to be bigger than velocity 1. All right. Now, the pressure in the big fat pipe, we'll call that pressure 1. And that's the energy density of the water in the big pipe. Now, that's potential energy density. In addition to potential energy, the water's moving, so it has kinetic energy. And potential energy for a single object is 1/2 mv squared, but here we're talking not about one object, we're talking about a fluid, and so the mass isn't a chunk, it's rather a density of mass. So rho is mass density, and if instead of 1/2 mv squared I use 1/2 rho v squared, this formula is now kinetic energy density. It's not what would have been just kinetic energy if this were an m. Anyhow, the same math works for the narrow pipe. So pressure 2 is the potential energy density, and then velocity 2 squared times rho times 1/2 gives you the kinetic energy density. But according to the conservation law, to the law of conservation of energy, the total energy before and after must be equal. Well, if the kinetic energy density on the right side is bigger, then the potential energy density has to be less. Otherwise, the equality won't work. All right. Well, that means that the pressure has to become less when the velocity gets bigger. Or what I wrote here is that if the velocity gets bigger, the pressure must get smaller. Anyway, that's Bernoulli's law, or Bernoulli's equation. And you saw it in the simulation, and okay, that's pretty interesting. And this has many applications, and maybe the one that's the most famous is in airplanes. So airplane wings have typically have a shape where it's more flat on the bottom and more curved on the top. When the wing, this wing is actually uh, moving to if the in this picture the airplane is moving to the left, but we're actually sitting like right next to the airplane, and so from our point of view, the air is flowing to the right. And one of the one of the things that airplane designers attempt to do is to make it so that the air, as it gets sliced by the wing, uh, uh, gets evenly lifted up over the wing, and also the air that's a little bit lower evenly goes below the wing, and the air molecules that, let's say, were here and here when they started out, they after that they're going to be here and here together. These two air molecules are like friends, and they say, okay, see you later, and one goes above, the other one goes below, and then they come back to you. Oh hi, okay, we're together again. But the point here is that this air molecule traveled this way, which is a little bit shorter than the upper molecule, which took a detour above and below. So since the upper molecule went further, it had to go at a higher speed to rejoin its friend down below. So, okay, to finish this explanation, if this one, the one that went above, went at a higher speed, that means that the pressure, which here I called P2, oops, hang on, the pressure which I called P2, this pressure, is going to be less than the pressure at the bottom of the wing, which I called P1. Or putting it the other way, pressure 1, which lifts the wing, is stronger than pressure 2, which is pushing down the wing. So by just having this difference in pressures, which is coming from the difference in speeds of the air below and above, you get the airplane wing feeling a upward lift, an upward push. Now, airplanes get lift from other effects, such as having the wing be tilted like this. If you tilt the wing like that, that's called increasing the angle of attack. And actually, that's where most of the lifting power of the wing comes. But um, but this type of lift is very efficient. It doesn't give a lot of lift, but you get almost for free. You get an extra lifting power, and that's really good. Now, uh, it, the idea that the idea that the air molecules that were next to each other here and here are going to actually end up back together again depends on the air flowing very smoothly over and below. And this can be messed up. So, for example, if there was a little bump in the wing, then the air will do this sort of thing. And this is called like a vortex or turbulence. And as soon as you start getting this kind of thing happening, it messes up the idea. It messes up this laminar flow or smooth flow. And in fact, the airplane designers take advantage of that. If you ever are traveling in an airplane, look out the window when when the airplane is coming in for a landing, usually the airplane has to fly pretty high over the populated areas, and then when it gets to the airport, it has to come down quickly. But the wings are lifting up the airplane, so you got to somehow make the wings not work. Okay, we can do that. There's usually a thing here that a thing here that comes up. They sometimes they're called air brakes, but not only do they slow the airplane down, but it causes the air to go and do this turbulent motion, which makes the wing not work so well, and the airplane can quickly lose altitude without having to like take a dive or anything. It makes for a level flight, losing altitude in a way that's comfortable to everybody in the airplane. So anyhow, I hope this made sense to you, and I hope that you will now do your homework. So yeah, I'll see you soon. Bye-bye.
It's interesting, huh?